Hello. This is a recorded lesson on an introduction to logarithms made by Scott Cheatham, a teacher with the Richmond Hospital Education Program. And if you are either someone that has already learned about logarithms or previously learned about them, this would be a nice review for you. But for those of you that are just getting into some of the more nitty-gritty aspects of logarithms and how they get used in trigonometry or calculus, this is going to be a great lesson for you as you move forward in your math career. For those of you that have already taken Algebra 2, you start to see some of the graphs of logarithms, but you don't really get too much into really what a logarithm is, why we use them, and how they get used in real life applications. So we're going to move forward and look at some of the rules for logarithms from here on. Well, if I gave you the equation 2 to the x equals 4, you would hopefully be able to determine that, okay, well, x is 2. 2 squared is 4. And it's kind of working backwards, just kind of asking yourself, okay, well, 2 to what power would be 4? It would be 2. Same idea would be if I gave you 2 to the x equals 8. 2 to what power is 8? And that would be 3. But if I gave you 2 to the x equals 7 and asked you, okay, well, 2 times itself, how many times is 7? It doesn't come out to be a nice even integer. And so you have to, it ends up being a long, messy decimal. But there are going to be times where being able to write that exponent in a more clear way is going to be helpful to us and something we want to do. And so rather than writing it out as the long, messy decimal, we wanted a way to write that in terms of kind of other numbers in a more easier to manipulate way. And that's why we use logarithms. And so for the definition of a logarithm, we're going to have if b raised to an n, so if a base, that's what b stands for, raised to an exponent n, equals m, we can rewrite that as log with a base b, log of that value equals the exponent. And so really what a log does is it represents an exponent. Another way of thinking about it is just a way of writing an exponent that would otherwise be a very long irrational number. And as we start to look at these examples, we're going to kind of look at some different ways of doing them. Just want to point out that a rule is that the base of the logarithm will always be positive. If you think back to if you have negative numbers raised to certain powers, and you can flip back and forth between signs, and that's not something that we're going to do here. So as a general rule, the value of the base will always be positive. It can be a fraction, it can be a fraction less than 1, but it is going to be a positive value. Now, as we're moving forward today, I'm going to assume that you have a good understanding of the basic exponent rules that you've been learning since Algebra 1 and before. If you need to do a refresher on that, there's some other resources out there for you I would suggest to look at, because the way we're going to do these today is going to be primarily without the help of a graphing calculator, because we're going to be working with certain logarithm rules and just kind of some things that come from those. And so as we're rewriting them, we're going to need to be fairly comfortable with the basic exponent rules. And so if you're not, then that might be something you might want to review before you come back to this. Now, for these problems here that we're going to work through together, it says rewrite the following statements converting either from exponential to logarithmic, or depending on if you're given logarithmic, converting it back to exponential. So for the first one here, we've got 5 squared equals 25. And we understand that to be true, 5 times 5 is 25. So if I asked you to write that in logarithmic form, let's look at what that looks like. So the way we read this is log base 5 of 25 equals 2. And going back and forth between these is going to be something we want to feel fairly comfortable with. So if you look at this, the base on the left of 5 squared, the base is 5, and on the right, the base of the log is 5. So that base doesn't change. If you were going to kind of look at this, that base stays in the same aspect of the equation. The exponent is what is isolated. So 5 raised to the second, or log base 5 of 25 equals 2. That exponent is what moves back and forth. Another way of looking at that log, so 5 raised to what exponent, in this case 2, equals 25. That's how we go back and forth from writing these. So what I want for you to try is going back and forth between exponential and logarithmic forms for these next 3 on your own. So if you need to go ahead and pause this presentation, and I want you to, for number 2, write that in logarithmic form, and then 3 and 4, write it back in exponential form, keeping an idea that the base is going to stay the base, and then you're going to kind of flip around those exponents and what they equal. So go ahead and pause the presentation now, and then start it back up, and we'll look at the answers. So here, I had mentioned before that the base of a logarithm was going to always be positive, but we can't have negatives in other aspects of the equations, and so 2 is one of those examples. So the way I would read that, log base x of 7 equals negative 2. And again, that's saying x to the negative 2 equals 7. We've kind of flipped back and forth between these two forms here. Now, number 3, 8 raised to the negative 2/3 equals 1/4. And if you actually work that out in a calculator, that's a true statement. That's something where you could, and this kind of goes to why I said you need to make sure you feel comfortable with exponents. That would be the same as taking the cube root of 1/8 squared. And so, again, that's the same as taking the cube root of 1/64, which is equals 1/4. And so as we kind of look at these, we're going to want to feel fairly comfortable in how we can write those and how we can go back and forth if we have radicals or if we have negative exponents, or playing around with these on our own. It's going to be important for us to feel comfortable with that. And then the last one here, we have only variables, and that's okay. So we have m to the y equals x as another way of just writing that around. And so really number 4 is a good example of what hopefully you will get to feel very comfortable with about what we're going to flip-flop on each side of the equation, what we're going to move up. We want to feel very comfortable with rewriting between these two forms. All right, now for these next 4, I'm going to walk you through the first 2 first before I kind of let you go as you would. But what I want you to do, actually, for number 5 there, I want you to write that in a logarithmic form based on what we had just done. Again, you got the space on the guided notes that you may have printed off, or you're just going from this. But go ahead and rewrite that as a logarithm, and this is a little bit of a unique circumstance. So go ahead and write that one how you think it might look. So hopefully, based on the previous slides, you wrote it as log base 10 of 1,000 equals 3. And that's true, 10 to the 3rd equals 1,000. But this is a unique case where we actually don't write the base. If you see log of a number and you don't see a base written, we assume it is base 10. Just like in square roots, if we don't see the number there in the radical, we assume that that's a 2 there. If we don't see an exponent, we assume it's 1. Logarithms, actually the number that you assume the base is 10. And so on your calculators that you may have been playing around with a log button for up until this time in your math career, if you ever hit the log button, it defaults to a base of 10. Now, there are some ways on some graphing calculators, or if you're using Desmos, to change that base. But when you press the log button, it defaults to 10. And it's considered redundant to write out that 10. So if you ever have a base of 10, we're just going to write log of the number and understand that the base is 10. Now, for number 6 here, we see this lowercase letter e. And e is a constant in mathematics that you probably haven't had as much exposure to as other constants such as pi. But it's an irrational number. It's about 2.718, and it keeps going. It's an irrational number. What e represents is something that you get more into in calculus. Where that number comes from, you don't need to necessarily worry about right now. But it does have a number of very specific characteristics that come up in calculus, and because it's so prominent, it actually gets its own special logarithm. So let's look at what this would look like if we wrote this in logarithmic form. So rather than writing log base e of 7.39 equals 2, what we write is ln. And again, if you've looked at your calculator, you've probably seen the log button, you've probably seen the ln button. And actually back in Algebra 2, the ln button, the what we call the natural log, was actually the log that you probably used more when you were doing some graphing. And so really what this means is the ln, sometimes it gets read ln or natural log, but it basically means that it's a logarithm with a base of this letter e. So when you see that, again, like I said right now, especially if you're just getting into trigonometry and some things like that, you don't need to worry about where e comes from. But we do that is a very popular type of logarithm that's going to keep coming up as we move forward. So for 7 and 8, go ahead and give those a try. How would you write those? And let's see, understanding that sometimes there are these understood bases. What would that mean, and how would that impact you writing those logarithms in exponential form? So go ahead and pause this here and work on 7 and 8. All right, so for number 7, we understand again that if we don't see a base, the base is 10. So we still would move that base up. So that base of 10 to our exponent of 2 equals 100. And that's correct. 10 squared equals 100. So that's something where just another way of writing it. But again, understanding that if we don't see that base, we're going to use a base of 10. For 8, the base that we don't see there is an e. So we bring up that e raised to our exponent of 2. E squared equals e squared, which is a reflexive statement there. So both of those are true. Again, we're just working back and forth, just happen to have some unique aspects here. Now, if you haven't printed, or if you weren't given the blank note sheet, then for the next few here, you might need to kind of just go a little bit slowly. But what I would say here is on the blank note sheet, there is 9 through 17 are some different problems where you are taking a log and solving for it. Now in the instructions there, it says if a log is an expression, as these first two are, set it equal to x. So let me show you what I mean by that. So if you're given log base 2 of 1 over 8, we need to be able to change that to an exponential statement. So here's what it should look like. Now sometimes you might be given an equation that already has x or some other variable in it, but in this case we weren't. So we're going to set it equal to x so that we can rewrite these as an exponential statement and then work through solving them. I do want you to try these for the most part just without using a graphing calculator. If you need to use a calculator to play around with some exponents, that's fine. But this isn't something we want to plug in the calculator. I want you to rewrite it as an exponential statement and kind of work through, okay, what does that mean with these based on these exponents. And so some of these might be a little bit challenging for you. It takes some practice to get used to rewriting some of these and how we might rewrite them. But it's something that as you keep going, you'll get more comfortable with. And if you have a hard time with this, then it's something where you can kind of walk through with me as I explain them. In your basic trigonometry class, you'll oftentimes have a graphing calculator, so some of these foundational things you'd be able to work at on your own. But especially for those of you that are going to go on to calculus, understanding how these work without the use of just plugging in a calculator is going to be an important skill that you'll keep learning now and keep using in calculus. So if you want to work ahead and go through the rest and then come back and hear me talk through them, that's fine. Or if you just want to kind of go through a couple at a time, that's fine also. So I'm going to let you go ahead and pause it here if you want to move ahead, or just do these two, and then we'll come back and go over them together. All right, so for both of these, I think the first step that you want to feel comfortable with is just the second line. So for number 9, rewriting it, bringing up that base of 2 raised to the x equals 1/8. And then for number 10, 1/9, the base raised to the x equals the 4th root of 3. Those steps, if nothing else, I want you to get and feel very comfortable with. Now the rest of this is what takes a little bit of kind of practice and some more advanced comfort level with rewriting things using exponents. So if you look at number 9 there, we have 1/8 equals 8 raised to the negative 1, and that's an exponent property. How we can rewrite 1/8. And the reason why I want to do this is it's a property of kind of exponents. If I have a base raised to a number equals that same base raised to a number, I can set those equal. So on the left side here, my base is 2. On the right side, my base is 8. I can't do much with that. But if I could get a base of 2 with an exponent equals a base of 2, then I can set some equations equal. So I know that 8, rather than writing 8, I can write 2 to the 3rd. And so 2 to the 3rd raised to that negative 1 is how on that last line there I've got 2 to the negative 3. And so if I've got 2 to the x equals 2 to the negative 3, then I can set my exponents equal, and I get x equals negative 3. For number 10 here, again, rather than having 1/9 to the x, I can just bring that 9 up and make it negative. And then I went ahead and rather than keeping it as a radical, I rewrote the 4th root as raising something to the 1/4 power. And so both of those are things that we're going to, hopefully you recall from back in algebra. But again, I want to get the same bases here. So it's going to be easier in order to do that, to change that 9 to 3 squared. And so when I do that, 3 squared, I got to multiply those exponents. So I get negative 2x would equal 1/4, setting my exponents equal, and then x equals negative 1/8. But again, the most important thing from here is feeling comfortable with that first step, rewriting in exponential form. If some of these fractions and kind of more advanced kind of working with exponents is throwing you, that's okay. It'll take some practice and you'll get it down. Again, if you need to pause here to work on these ones, you can. Remember for number 11, we're going to need to set it equal to x. 12 is already an equation, and so we don't need to do that for that one. But again, we're going to kind of manipulate it right into exponential form. So if you need to pause, go ahead and do it. So for number 11 there, actually I think this one's a little bit easier than the last two we had. We have 4, we set it equal to x, so 4 raised to the x. Again, I want the same base in order to be able to set these equal, so I'm going to rewrite the 4 as 2 squared. And then the 2, I'm going to think of it as 2 to the 1st, and that gives me the same bases. Then I can set my exponents equal, 2x equals 1, and solve at x equals 1/2. For number 12 there, when I rewrite in exponential form, I get x to the negative 2 equals 1 over 25. I want to bring up that 25 And when I do that, I can rewrite it as, well, x to the negative 2 equals 5 to the negative 2. And this is one of the first ones where we're not trying to get necessarily the bases equal, but if we get the exponents equal, then I can set my bases equal. So if I know that these two things are equivalent and they're both being raised to the negative 2 power, then I know the bases, even if they're written differently, have to be the same. So in this case, x equals 5. So again, if you need to pause here, that's fine to go ahead and pause, and then we can come back to it. So if you need to pause, go ahead and do that now. Now for 13 here, we are not given what our base is. And so hopefully you remember there, if we're not given the base of the log, we assume and understand that it's 10. So when you're writing that and you're rewriting it, make sure that you understand and write that that base is 10 when you're writing in exponential form. So when we do that, we do 10 to the negative 3 equals x. This one we're really just kind of evaluating what we have here. So 1 over 10 to the third, or 10 to the third is going to be 1,000. So 1 over 1,000 equals x. Now here, this is where for 14, when that base is x, we're going to probably be looking to we're going to want to see if we can get the exponents to be the same, to set the bases the same. We get x to the negative 2 equals 36. So when we do that, what I ended up doing is, if you look at this, we had x to the negative 2. If we raise that to the negative 1/2, that's going to end up canceling out the exponent over there on the left. It's just going to be x. But whatever I do on one side, I have to do the other. So take it to the negative 1/2 there, which is the same as doing the square root of that reciprocal. So the square root of 1 over 36, x equals 1/6. One note there, normally in algebra that would be plus or minus 1/6 because we added that square root, but because the base has to be positive, the answer is just 1/6. All right, so for 15 here, again, we got another log where we're trying to solve what is the base. 16 is our first time we've had a natural log, and I will say that one is one where if you typically can leave things with using e, just like you can leave things using pi. But if you did want to figure that out as a decimal, it is an irrational number, so it is something that's going to be a little messy. That's kind of the only one we've had where you might need to use a calculator if you want to get a final answer there. So again, rewriting it, x to the 2/3 equals 16. Then I just want to get rid of that fraction exponent there. So if I raise it to the reciprocal, 3/2, I'm going to multiply those and it'll cancel out and give me x to the first. Again, whatever I do to one side, I got to do to the other. So 16 raised to the 3/2. A couple different ways you could think about this, but we're going to think that 2 in the denominator is going to be meaning the square root. Then raising it to the third, the numerator. So we get 4 to the third, or 64. Again here, that should have been plus or minus if it was just a basic algebra equation, but because we're dealing with logs, that's going to only be positive. For the natural log, for 16, again, honestly, if you left it as x equals e to the 1/2, that'd be fine, or the square root of e. Both of those are acceptable in terms of leaving your final answer. If you did go ahead and plug it in a calculator to see, you would end up getting 1.65, and it keeps going. It's an irrational number. But for the most part, we're going to just leave it in terms of e. All right, and for 17, our last one of these practice ones that we have log base x equals -2. Now for this one, if you've already done it or if you haven't done it yet, we do want to leave it in radical form, so not a decimal. Like I said, I want you to try these without a calculator. But make sure that you do rationalize any denominator. So if you have a radical in the denominator, which you are going to have at one point here, make sure that you've taken care of that and simplified it as much as possible. And so that might take you back to some other skills that you might have not been thinking you would use here. But so go ahead and pause and make sure that you don't leave any radicals in the denominator and you've simplified it as much as possible. So here, x to the negative 2 equals 12. That's just rewriting an exponential form. To get rid of that negative 2, I'm going to raise it to the negative 1/2, because then I'll just be x to the first. But 12 to the negative 1/2 does take some cleaning up once you have it. So to the negative 1/2 is going to be 1 over the square root of 12. Now you might have not done it in this order, and that's fine. But again, square root of 12, 12 is 4 times 3, so I can reduce that to pulling a 2 out on the outside. I cannot leave that square root of 3 in the denominator, so we multiply it by square root of 3 over square root of 3. That gets rid of the radical in the denominator, turns it into a 3, and multiplied by that 2 gives us the denominator is 6. And then we get the square root of 3 up at the top there. That one is definitely the more complicated one that we had. And some of the examples that I have in this extended practice might look like that, and you might be a little bit too much for you. I'm also going to provide you with the key, and so you can look at how I work out some of those extended practice ones. And so if you are a little rusty at some of that, that's fine. Main thing we want you to pick up now to build off of is rewriting things from logarithmic form to exponential form, and then you can kind of build and practice from there. So on the blank note sheet there, it's called classwork, and something that I just want to provide you some extended practice to do at your own pace. I've also have the answers that I will provide with this presentation. Me working them out. It may be how you did it, it may not. And again, I encourage you to try and do it without a graphing calculator. We haven't talked much about plugging logs into graphing calculators or Desmos. You can certainly do that on your own if you want to practice that. But especially for those of you that are going to be moving on into calculus, being able to manipulate these logs and exponential expressions is going to be a skill that's going to be very important for you. And so I would encourage you to at least give it a try first without a calculator before moving forward. If you feel like you really need to go back and refresh some of those exponent rules, that might be something you want to do. But as we move forward with logs, those exponent rules are going to be even more important. Because as we said, logarithms are really just another way of writing an exponent. So all the exponent rules that you started learning in middle school and in Algebra 1, they're going to come up here and be used throughout this. So I thank you for listening to this presentation. Good luck with the classwork. The challenge problems, again, those are designed to be hard. They're something beyond the scope of what you would really need. But if you just kind of want to see how some of these get used a little bit more complicated, you can see that. And I thank you for listening. I wish you well. Goodbye.